But today I was asked to give you a brief introduction into water services, how they function and what kind of issues there are that digitalization would help with. And then I will go a bit through more truly through the implementation issues and various challenges regarding the implementation of digitalization and show a couple of nice examples. Half an hour is rather short time, so it will be a bit high level. Nonetheless, let's start with water supply systems. As you know, they cover really large areas. They can be thousands of kilometers of pipes in bigger cities. Usually they are connected in multiple loops, so the pipes make all kind of circular connections between each other, and they are buried there 1 to 4 meters below the street levels. They are pressurized, so the pumps always generate some pressure into the pipes to ensure that no pollutants can enter the pipelines and that the water flows through the pipe network. So this line presents the pressure level in the pipelines. Often the water is produced somehow from groundwater sources or surface water purification process, and it's pumped into the networks. Perhaps there is a water tower or several water towers that even out the changes in water consumption, and then some pressure booster stations to ensure that even in the edges of the network there is enough pressure so that your showers and washing machines and all that kind of water appliances work. Often there are very few measurements in the network. Sanitary sewers work pretty much the same. As the water has been pumped there for your use, then it enters the sinks and toilets and so on. It flows gravitationally through the pipelines that are similarly deep in the ground. They are only partially filled, and every now and then you have to have a pumping station that increases the pressure so that the water can be lifted over hills and transferred longer distances in lines if there is not enough elevation differences in the ground. And finally, the wastewater enters the wastewater treatment plant, is purified and released back to the nature. The nice thing with sewer networks is that they are more simple. They are tree-like, so usually there are many connections coming into one manhole or this kind of well, and then one pipe going off. And as they are not pressurized, the pipes are only partially filled with water, then they are easier to inspect. But the conditions in the pipes are harsher. There's a lot of suspended solids and biofilm accumulation, these kind of issues that have to be remembered if we install any sensors. Well, those pictures were rather simplified. So here's one example of a medium-sized Finnish city. So it's 1 kilometer by 1 kilometer area of part of the water distribution network. There are something like 400 connections here for the households, mainly block houses and whatnot. The colors here present how many times a day the direction of flow changes in the pipe. So you can see that there are many pipes where the direction changes something like between 5 to 10 times or even more in a couple of pipes, even in this kind of small area. So it's rather hard to know what is really going on there in the network. And it's even worse when you see that what is the difference between maximum flow during the day and the minimum flow. So there are several pipes where the differences are 15. So the maximum flow is 15 times higher than the minimum flow. And these are the challenges in managing the network, as you can't really measure everything, and the flows are really complex in water supply systems. Also, sewers are not as simple as one would believe, as there are also a lot of leakage, infiltration and inflow coming from the soil, surface water, so rainfall, snow melt, this kind of waters entering even the sanitary sewers. And in many bigger, older cities, the sewers are actually combined, so all the storm water is actually coming to the very same pipes purposefully as the sanitary sewage. And in those kind of cases, there are usually a lot of overflow structures, so that if a major storm comes, then some of the stormwater sewage mixture is released to the sea or lake or river, so that the basements are not flooded and so on. So, and measuring flows, for example, is hard in partially filled pipes. And as mentioned, this kind of biofilm accumulation and whatnot also cause issues with sensory. A few words about the problems that the utilities face all around the world. So even nowadays, you have to remember that there are something like 2 billion people that actually don't have access to safe water, and more than 3 billion people who don't have access to any kind of proper sanitation. And something like 2.5 billion people live in the countries where you don't have enough water regarding the actual need. So water-stressed countries. That's the kind of harsh reality, and it's getting worse every year, as you know, due to the climate crisis. But regardless of the availability of the water, all the utilities all around the world face same kind of issues. Aging infrastructure, the pipes are getting in worse condition, and that causes various other issues like leakage. Outside of the pipe, you lose some of the potable water, infiltration, so excess water entering your sewer systems. Water reserves are dwindling, there are floods. The deteriorating condition causes water quality issues in the network, but also the kind of chemicalization causes a lot of issues for the raw water sources that are used for creating the potable water in the first place. There are plenty of different vulnerabilities and risks that ought to be managed properly, but rather few utilities are actually having the right set of tools for that. The same goes with the overall management of the utilities. They are often, let's say, not optimally managed, and a lot of the decision making is based on bit ad hoc mentality instead of this kind of knowledge and data based management practices. There are a lot of financial constraints. That's also one reason why the networks are deteriorating, as the utilities don't have enough money for investing or into all the rehabilitations. And usually the price increases, energy price increases, salaries, everything grows much faster than the price of the water. So the utilities are more and more burdened. And urbanization, of course, brings more people into the cities. The infrastructure must cope with the all the time growing population, with more and more of the surface area covered by asphalt and concrete. And at the same time, there is deruralization happening, so emptying of the countryside. That also causes other kind of issues there, where people leave the cities and towns, villages outside the big cities. Managing those kind of networks is a completely different thing. Climate crisis was already mentioned, but also human resources. So all over the world, the utilities are struggling to find the best possible experts and more experienced workers to do the work that is needed. There are not enough people coming. People are growing older that are already working at the utilities. They are going to pension, and this kind of knowledge transfer for the younger generation is also very critical. And due to this kind of financial constraints, of course, all this efficiency of operations must be increased somehow. And there's one more thing, that the leakage from the networks is usually something between 5 to even 60% of the water pumped into the network. That amount of water is lost before it gets to the people. And if you don't have enough water to begin with, and you have to treat the water, but you don't get any money for that, that causes some of the financial issues. And globally, the water utilities, the whole water sector uses 7% of the total energy consumption of the world. So it's a huge amount of energy being used here. Something like 22% of that energy is being used for pumping water and compressing the air in biological treatment processes. So there's plenty to do. And regarding the climate crisis, last year it was assumed that something like 9,000 people died due to the floods and flash floods, mud and whatnot caused by heavy storms or droughts. And these climate phenomena drove 40 million people from their homes, and altogether they caused at least $550 billion worth of damage. So that's probably the most important thing to do to try to avoid that kind of issues beforehand. One interesting thing with the water utilities is that when you have to be building this kind of network over the time, when the cities grow, the situations change, it actually causes a thing called path dependency. So we stand somewhere today regarding what we have, the amount of invested money in the networks, and usually there's something like 80 years or 120 years of history or something in that kind of range. Every day, multiple decisions are being made at the utilities. Once every now and then, there comes a major decision, whether we are going to build a new treatment plant, whether we are going to expand the network here or there, what kind of major pipelines we are going to build to transfer the water between different areas. Often you have a couple of choices. The number of choices is very much limited by what we already have and how the city is going to grow. And often you don't have all the information that is required to do those decisions. You make some decision, you choose one plan, and then for the next 20, 30, 50 years, you have to live with the result of that decision. You invest money in the network, and then after a while, there comes time for another decision. And then you are again working with what you got. Then you make another decision, and so on. And then, of course, at every single point when decisions are being made, we have to kind of assess and analyze what is going to happen in the future. And of course, nobody really knows. And the more data, the more knowledge, the better decision support systems we can provide for the utilities, the higher quality decisions, of course, can be made. The thing is that about 80% of the whole life cycle costs of any systems are decided in the first phases of design, when you make the rough initial sketches that this is the plan we are going to execute. Then you already have locked 80% of the costs. And afterwards, you just operate the system. You can make minor adjustments, but they will only have maximum effect of 10, 20% to the total costs. So focusing on the planning phase as early as possible, that saves a lot of money and makes the systems more reliable and robust. Typically, the pipe life is something between 50 to 80, even more than 100 years. That's how long one pipe is surviving in the soil. Quite often, these decisions are being made a bit in the dark. And one reason for that is that while 80% of the assets of water utility, all the investments being made is in the networks, at the same time, 85% of all the measurements are in the plants. As the network is just so huge, you can't really install that many old school sensors, at least, that require electricity and proper communications with a lot of space requirements and electricity requirements everywhere in the city, under busy streets and so on. So those kind of measurements are not existing. But of course, with modern technologies, the sensors are getting smaller, batteries are getting better, communications are getting easier. So it becomes more and more possible to install more sensors, but never we can measure everything that we would want to do. And that's why the networks are pretty much black boxes. Luckily, there are solutions like modeling, machine learning, this kind of stuff we can use to understand better what is happening in the networks. And that's the next topic. So what we actually aim usually when we talk about smart water and digitalization of the utilities, it is to give you some kind of insight what is happening and what will happen in the system and how the different alternatives compare to each other. So this is how the system actually looks like when you look at the city. But what we would like to have would be kind of binoculars. You can see under the streets and understand the condition of the pipes, functioning, the importance of the different components. And we, of course, try to get there in order to forecast, prevent, and quickly detect problems, understand the system as a whole, preparing and analyzing the future scenarios, what-if scenarios, preparing for exceptions, and optimizing everything from operations, chemical use of workforce, CO2 emissions, and so on. And I guess for this audience, knowledge management is rather familiar term, but the idea, of course, is that we go from raw data to information when we enhance the data, combine it with different sources, and from information we go to knowledge. So we get understanding of how the system behaves, and then we can start make some decisions based on that knowledge we gained. But often we only have access to the raw data, and the other steps are either impossible or really time-consuming to do. Amount of measurement points and sample sizes, of course, grow when we go towards the raw data, but the value and the benefits get much bigger as we go towards the decision and also the implications. And all decisions, of course, should be made against the strategy decided by the utility or the operational needs by the utility. So in practice, with this kind of circle, we make an analysis of the situation where we are, and we have an idea where we want to go. We design, plan preliminary some interventions, and then we try to assess which works the best, make a decision. This is the alternative we are going to implement. And then after it has been implemented, we evaluate how well it worked. Then we keep monitoring the system, and when we start to notice that something needs to be done, the circle starts again. And that's what knowledge management is in the water utilities. But it's not so easy, of course, as the water utilities have very many different kind of departments and operations that are siloed. So on one hand, you have the people you're using the water and the customer support, and on the other hand, you have the like management. You have the big bosses, the leads of the different departments, the board, the owners. And then you have the production side, where you have the operators and managers who work at the office. And then you have the construction maintenance guys working with the equipment on the field. The same goes with network side. So those are the people who are actually really there on the streets. Your operators again and managers usually work at the office. It might be other building than the other departments. And then the construction maintenance workers again, the plumbers, they work there on the streets. And then usually there's some kind of a planning section, planning department. There might be different people for planning and for the production side and the network side. And then often a lot of consultants are being used, as this kind of special expertise is not always available at the utilities. Well, how then this goes in practice? Everybody tends to see their own side. The people only see the water coming or not. They see the invoices. Customer support is usually only contacted by unhappy people. The bigger bosses, the management, of course, is interested more in the money, some strategy things, maybe some climate change goals and whatnot. But it's probably, especially when it goes to owners and board, they are not really interested in that much of the day-to-day operations. The production side have their own systems. SCADA is the main tool they use for monitoring and controlling the system. And of course, the worker, they work with the sensors, the pumps, valves, this kind of practical kind of lab equipment. And then on network side, the people, the operators, they usually use the network information system where all the digital information of the network is collected. And of course, then the construction workers work with excavators and shovels, and they are welding the pipelines together and so on. And then in the planning section, there's a lot of variety of the tools. It might be AutoCAD for making the drawings. It might be some modeling software to understanding the system. Excel is probably one of the most commonly used tools. And the planning side is usually the place where all the information from the management, the upper management, from the network, from the production, from the general public, from the municipality and authorities, all that information needs to come together in order that the plans can be executed. So usually the data needs, they are the highest in the planning side. And they are usually the people or the department that has the best ability to take new systems, new solutions into use. And the one extra complication in the water utilities, of course, is that the systems they use, they form kind of hierarchy that is also tied to the cybersecurity things. Not only cybersecurity things, but you have physical security, the physical devices, and this kind of need to know basis. Not all the information can be shared publicly, especially these days. For example, the NIS2 directive changed a lot of the things regarding this. All this kind of cloud computing things, they are changing the matters here. So there in the bottom level, you have the physical system that actually can cause harm. You have the physical machinery, the valves, the mixers, the pumps, the motors that can actually be even dangerous, and they interact with the physical real world. Then there is the critical control systems. So some kind of programs, the SCADA system perhaps that drives that all, and monitoring equipment, so that usually have some kind of sensor, some kind of data transfer, so that the control system can operate based on the kind of measured feedback from the system. These form the most critical systems, usually the most separated, best protected environment, and that's the way it should be. A lot of valuable information is collected here. And if you want to, for example, optimize the production, optimize the distribution, you would probably also need to feed some information back here. But understandably, making any kind of machine-readable connections to there, it's a bit more complicated than normal. These are of utmost criticality to the utilities. Then on top of that, usually we might have some higher level control, including these kind of manufacturing execution processes, the optimizers, let's say inventory tracking, chemical tracking, so on. And then we have the reporting and planning systems that use the data coming from the monitoring side, maybe command or use some data from the higher level control thing. And then you have all the kind of office software you need, the network information systems, various tools for making dashboards, data analytics. You have the CAD software, whatever drawing software you need to have, and so on. This is the space where I see that you have the most space for doing the smart water. Of course, there are a lot of physical things like new sensors. There are a lot of new monitoring devices and technologies regarding the data transfers and so on. But this level where you start from half of the monitoring side, like the automatic water meters, and then you can have some additional nice to know information collected in the network that is not mission critical, but helps the utility to serve the public better. This is where we can add a lot of stuff. This is where we can combine the data coming from different sources, fuse it to produce some kind of new knowledge. And this is where it has the biggest effect on the workings of the utility in preventing problems, forecasting the future, providing the proper ways to assess the alternatives. Then finally, there are even more nice to have systems, some early warnings, some trend following systems, some automation, for example, reporting to the authorities and so on. And finally, we have administrative and governmental systems. So the utilities all over the world usually have to report a lot of data to environmental authorities, to health authorities and so on. And there is good place for adding new APIs, automating things. So for example, just the other day, one of my good friends working for a big utility was a bit proper word, not too happy of the amount of work, how she had to combine information from 5 different systems, manually copy pasting things in order to calculate the key performance indicators. She had to manually type into a governmental system for reporting. But could this be automated anyway? Yeah, probably it could. I marked here the places for the, I would say, the most important interfaces and where they are possible to have. So between some part of the monitoring and reporting, high level control to the planner software, reporting software, and then of course all that kind of nice to have quality of life, the very high level automation and governmental systems is something that probably could even be run in the cloud. It's not mission critical. But these days, I think the tide has turned. Now everybody talks more about edge computing. A lot of the utilities are actually starting to introduce private clouds and so on to actually get a bit away from the cloud again. As we see that the cables are being broken. Amazon, for example, has, I think, at least 2 or 3 times a year, something like 60% of the internet is offline because of some misconfiguration or some incident happening at Amazon services or at some US network provider. So this is sometimes, or it is unacceptable when we are talking about critical infrastructure that can really affect people's livelihoods when we talk about flooding, for example, and health when we talk about sewage, and health when we talk about the water quality of the drinking water. And then besides the aforementioned thing, there are a couple of other issues that pop up all the time. There's one other one I didn't add here, but I will mention it, is of course the slowness. So everything takes usually a lot of time. It's a lot of people, a lot of operators like ICT connection providers, some ICT service providers, probably different people than the operators. You need to have the control system providers, the other vendors, then the water utility people from the different departments coming together in order to move any projects together. So it's even these days, if I make a very conservative estimate that yes, getting through this kind of project is, let's say, half a year thing to get everything working. They still usually tend to go all of like 1 year long or even longer sometimes. And it often happens that somebody can do the work on time and the others wait, and there's holidays, and then when the thing is done, the other people are already working on something else, and then it takes time for them to come back. And this kind of scheduling risks are surprisingly large. And one reason for that, and one reason why water utilities are not so digitalized yet, is that there are gaps in deep understanding of technology and sometimes gaps in ICT capabilities in the utility. You have very expert people working at the utilities, but it's rather rare to have that kind of, let's say, smart water knowledge management background people who actually would have the capabilities and the deep knowledge of the domain to introduce good good practices there. And the data that the utilities have had, especially historically, is usually not necessarily low quality, but let's say not of the best quality at least. A lot of data is missing, non-existent. It might be only available in some archives in paper format and so on. And it's rather rare that there are already APIs or programmatic data access available to any of the legacy systems. So for example, the control systems being used and reporting systems being used in water utilities, they are typically renewed, let's say, every 25 years. So they tend to get rather outdated, rather not the easiest to work anymore, as they are very slowly replaced. And this must need to be taken into account. Also, the administrative systems, they are often rather legacy. And also due to the lack of the deep understanding and this kind of departmental siloed structure in the organization, there often is lack of strategic approach. So there is not necessarily a digitalization strategy or, let's say, data management strategy or best practices. Nobody really owns any of the systems. There's no inventory of the available data. And that often leads to this kind of ad hoc solutions, the different departments competing with each other, parallel systems being developed for the same purpose. And sometimes I have even seen this kind of a blocking the other departments of doing something because we don't want to pay, because we don't need that system. And this kind of organizational issues, I would say, are often kind of bigger roadblocks than the actual technicalities. Technology is easy, money is something that we can solve, but the kind of organizational training and changing the mindset into that kind of knowledge-based management kind of thing, it takes a long time, and not too many utilities are really far on that road yet. And then, of course, there is the fact that usually the utilities are understaffed. Everybody has much more work to do than they actually have time for, and that causes an issue with activation energy. So in order to get there down where you have an optimal situation, you first have to climb uphill. You have to do extra work. You have to find information. You have to be finding out things, doing something besides your day-to-day job. So it's actually not really rewarding. It takes time and energy. But if you get over the hill, then life is much smoother again. But communicating this clearly to the people and giving the time frames that yes, for the next week, yeah, I know you have to pull long days, but then after a month, you will have the new system online and it will save you 1 hour every day. This is one of the key things. But okay, I'm about done. I will show a couple of examples of nice things that has been done on our side. And one thing I want to mention in the beginning, you don't need to have AI, you don't need to have machine learning. Sometimes the very basic things are the ones that help the utility most. For example, just calculating a water balance, how much water is actually being used in an area, combining the different measurements you have there. And especially if you can provide a forecast like that dashed line over there shows. So it's the forecast what will happen over the next 24 hours. That's what helps the utility to operate and understand the network behavior a lot. Here also there's a green line behind the blue line, that is the actual measurements. The green line signifies what is the typical usage at this weekday, at this time of the year, at this time of the day. So you can immediately see if there is something wrong with the water consumption in the area, a potential leak or something like that. Helps a lot. And one thing that the same friend I mentioned earlier was struggling a few days ago was how could I combine information coming from the groundwater elevation measurements. They are using many different systems for that. And that information needs to be connected with the SCADA data that tells how much water was being pumped away from the different groundwater wells. And in order to have any good understanding of that, you need to see that how much the water level in the groundwater well is declining when you pump more water. So in the right-hand side, we actually see a picture that during last month, level drop was higher than typically over the last few years at the same time. So for some reason in this specific location, there was actually less water available in the aquifer than normally. And this kind of data again helps the process engineers to do their job better. One nice thing we did that was actually a rather complex system where we have multiple parties working. It was done for one major Finnish water utility. We combined AMR data, so coming from the smart water meters, the valve statuses coming from the network information system, all the measurements we get from the SCADA and the control systems into a tool that can automatically detect leakage, now the pipe bursts mainly, the bigger leakage, and then automatically pinpoints where the leaks are, so leak localization, and then that data is automatically put through the whole chain of operations and into the network information system, and finally it comes to the tablet of the network operators and then the field workers. And it looks like this, that when there is a change in the demand pattern, we detect that there's a leak, how big it is, then the localization part starts, and finally this is the picture from the actual network information system in use. There you will see the most probable locations of the leaks, and then the manager of the network can assign that, okay, these 3 locations need to be checked, and it automatically comes to the network workers, the plumbers who actually work on the field, to their tablets, and they go and check and try to find the leak. And finally, one very interesting thing we did already years and years ago, a decade ago actually, it's a real-time quality model that's open for public. So this Vellamo is for Tampere water utility. All the time there's real-time digital twin of forecasting model calculating the hydraulic status and the quality parameters. And then there is a nice website where you can go and click an area, see what is the water quality right now over there, and then you can see historical data. And it has all the open APIs so that people can also integrate that into other software. So just a few examples what kind of things have been put. I also include here a few books, but they are rather high level, especially the Smart Grid for Water and this digital water book, but I have found them rather inspiring read. And if you are more interested in actually the process of planning and managing the water utilities, designing the water distribution systems and managing them, then Savici's and Bayard's water distribution system is, I would say, the best book on the field. But hey, thank you on my side. I guess I actually managed to exceed my time a bit, but I hope.
Yeah, but that was